After speaking with 500 plus students, teachers, and L&D trainers, we learned that learning is frustrating, expensive, and broken. Well, it's time for a change. Introducing Kplor, your personal AI tutor. Here's how Kplor will redefine learning.
Kepler is pretty simple. I tell it my basic details, my name, my university, department, and my semester. Then I tell it about what I want to learn, my proficiency in the course, my goal, which is just to pass the course, how much time I have left for the exam, which is in this case 2 days with roughly 3 hours per day. With this, Kepler creates a custom learning path where it pre-selects topics based on my time constraints. I am not clear with a few fundamentals, so let me select them as well. I want to deep dive into power function and quickly skim through exponential functions. I can also go above and beyond my curriculum, but let me drop that for now. With that, I am ready to go. For a more personalized learning, Kepler captures our face emotions and voice modulations.
Hi Sanjeev, welcome to Kplor. How are you doing?
I'm doing good.
That's great to hear. Sanjeev, are you excited to dive into your engineering mathematics course and explore the world of power functions?
Yes, I'm excited about it.
Okay, Sanjeev, let's start with power functions. So first, what exactly is the power function? Any function shaped like y equals x plus b raised to the power m and can be any real number except 0.
Wait, can you explain it in more detail?
Are you up for a more detailed explanation?
Yep.
All right, let's dive into power functions. You know, these are fundamental in calculus. Here's the deal. When we differentiate y equals ax plus b to the m power, we use the chain rule. Remember, m can be any real number except 0 for a, super important. Pausing for a moment. Let that sink in. First derivative time. Ready. Here's our rule d dx of x plus b m equals a rule m ax plus b m1. See how we brought down the exponent of the coefficient? That's the chain rule magic. Take a moment to write this down. It's crucial. Double derivative coming up. Now we get m times m. Would you like to take a small assessment in the power function?
Yes, I would like to take it.
Is the derivative of the function f of x equals to x to the power 5 equal to 5x raised to 4?
I think yes.
Great job, you got it right. The derivative of f of x equals to x to the power 5 is indeed f prime of x equals to 5x raised to the power 4. Ready to move on?
Yes, I'm ready to move on.
We are moving to the topic product functions. Ready?
Yep, I'm ready.
Let's start with the star of the show. The product rule. Imagine you have two smooth functions, u of x and v of x. When you need to differentiate their product, here's the magic formula. U prime of x times vx plus u of x times v prime of x. Take a moment to write.
Wait, I already know about it.
You are already familiar with this topic. Great. Now, would you like to dive deeper, get a quick summary, or move on to the next topic?
I would like to get a quick summary.
Okay, let us skim through the product rule. Imagine you have two functions multiplied together, say u of x and v of x. If both are differentiable, meaning smooth enough to have derivatives, we can find their products. Derivative to this elegant formula. The derivative of ux times vx equals sum of derivative of ux times vx and u of x times derivative of vx. But take a moment. We can take the assessment later in our learning journey. Ready to move forward?
Yep, I'm ready to move forward.
Welcome to one of calculus' most elegant tools. Let us answer the crucial question. How do we find high-order derivatives of multiplied functions? Imagine you have two functions, u of x and v of x, both differentiable multiple times. Quintessential. The theorem states their nth derivative is the sum of products each term. I'm combining lower derivatives of u with higher derivatives of v, weighted by binomial coefficients. Take a moment to observe.
3 hours later.
We are moving to the topic Leibniz's theorem. Ready? Welcome to one of calculus' most elegant tools. Leibniz's theorem answers a crucial question. How do we find high-order derivatives of multiplied functions? Imagine you have two functions, u of x and v of x, both differentiable multiple times. The theorem states their nth derivative is a sum of products each term. I'm combining lower derivatives of u with higher derivatives of v, weighted by binomial coefficients. Take a moment to observe the pattern. Hey Sanjeev, hope you are doing great. I noticed you seemed a bit distracted during the last video.
Yep, everything is all right.
Were you following along?
Yes, I was following along.
Great. Let us move to Leibniz's theorem.